One of the most useful constructions in working with Newton's laws is the free body diagram. So let's discuss that a little bit. Suppose we want to investigate the acceleration of a box pushed along a surface. Box, my surface. Here's the pusher. Okay, now this person is going to apply force on the box like that. Okay, the box might experience some frictional force, which is always going to be in the opposite direction. The box is going to have some weight. It's going to go down. And there's another thing which is here, which is the fact that the floor or the ground is pushing up on the box. This thing is called the normal force. So we're going to give these each a label. That last one is the normal force. Okay. This one is the weight. Friction. And the push. Now this is actually a rather complicated drawing. For one thing, there's a couple of different things that might be pushing and pulling. For example, there is this person. Okay, this person is obviously pushing on the box, but the box is pushing back on the person. So that's one body that might be interacting. There's this box, of course. That's what we're mostly interested in. There's also the floor, which is being pushed down upon by the box. Okay, so we need to simplify this. In some situations, we may be asked specific questions about specific other parts. So instead of having a box there, we're going to make a dot. Okay, and instead of having the forces going in all different directions, we're going to have all of the forces with their tails emerging from this dot. So, for example, the push force, F sub P, extends out this way. The frictional force, F sub little f, extends back that way. The weight, F sub W, extends down that way. And the normal force, F sub capital N, extends up that way. Now the next step in most of these problems is to separate the two dimensions of forces. So in this case it might be the horizontal components and the vertical components. Okay, and let's just call this the X and this the Y dimension. So I would say net F, the net forces in the X direction, is going to be equal to M times A in the X direction, and the net of all the forces in the Y direction is going to be equal to M times A sub Y. We can always do this with vector components. This sigma thing here means add them all together. So the sum of all of the X forces is going to be equal to the mass times the X component of the acceleration, and the sum of all the Y forces is going to be equal to the mass times the Y component of